Okay, now the next example corresponding to the positive flow stage will be the spherical propagating frame, right? And the right-hand side tell you this is a typical example to let you know the structure of propagating a spherical frame. Here, in the surrounding, there is a fresh mixtures. Okay, now you ignite the spherical frame from the center. That means the flame will propagate from the center to the outer surrounding in different directions. Then you can figure out there is the blue flame. This is the blue flame. Okay, propagating blue flame. And the inside of blue flame actually, because the flame is expanding, right? Expanding spherical flame. Then inside of the spherical frame will be the products. Okay, and the outer region will represent the fresh mixtures. Then this blue flame will propagate from the center to the older surroundings. Okay, this arrow represents the propagation directions of this spherical frame. And here you understand there is the position zone. Position zone usually is in front of the propagation frame. And this dotted line represents the boundary of your position zone. Okay. Now we still use the same idea described previously to think about the balance between the heat diffusion and the mass diffusion. Here you can see the heat diffusion will from the center to the surrounding, right? Based on the spherical coordinates, you will see this heat diffusion directions will start from a small region to a large region, right? You can examine it. For example, this is a flame region, high temperature region. They will diffuse your heat from a small region to a large region. The heat distribute from the small region to a large region. That means the thermal energy will be reduced in terms of unit volume sense. Okay, which means in this case, heat diffusion still give you the negative effect. However, the mass diffusion will diffuse from the free streams, the fresh mixtures, to the flame zones. That means identified by red arrows. This is the direction of mass diffusion. Mass diffusion will give you the mass from the large surface to be concentrated to a small region. That means the concentration of a given unit volume will be increased. Okay, this is a positive effect. When you look at this problem, as I mentioned, this is another example for positive flow stage. Okay, that means that they are the same in terms of flow convection. They are the same they have the same a positive flow stretch. In this sense, you can see the diffusion, the strength for for heat diffusion and mass diffusion give you the same effect. Okay, heat diffusion is negative, and mass diffusion is a positive effect. Then you can see they may have the same results. If Lewis number bigger than one, that means the heat influence is stronger than the mass. Unfortunately, in this case, the heat will give you the negative effect, but mass give you the positive effect. That means that you have a stronger negative effect overwhelm the weaker positive effect. Then the flame is weaker. The result is completely similar to the previous case for a flame propagating in a stagnation point flow. Similar way, you may have the same result. You can think about by yourself as the case for the Lewis number smaller than 1. The flame should be stronger as you try to increase your flame stretch. That means that when you have a propagating a spherical flame, for the case of Lewis number bigger than 1, the flame will become weaker and weaker and weaker. But for Lewis number smaller than 1, then the propagation spherical flame will become stronger and stronger as they propagate to the surrounding, to the fresh premixture. You may think in opposite way. Okay, the left-hand side, we are dealing with outwarding propagating spherical flame from the center to the surrounding, right? You may think, can we reverse it? Sure, you can reverse it. When you reverse it, you consider there is a fresh premixture inside of your spherical flame. but outer region actually they are complete burning already. Then the blue flame will move inside more into the center region. Okay, the direction this arrow represent the propagation of your blue flame. Now your preheating zone will exist inside of the blue flame, right? This is a dotted line. Now the direction of heat diffusion and mass diffusion completes reversed. Think about the problem as we described. This outwardly propagating spherical flame is this is a usual. You can see the ignition process, right? In the ignition process, you ignite a spherical flame, then they will propagate outward. This is a usual case we can see in real applications. In this case, flame surface is become larger. Then we call this as the flame is under particle stretch. Okay, but in this case, the flame actually is propagating inwardly to the center. That means the flame surface is continually reduced. Then you will think about this flame should be under a negative flow stage. It's under compression. Okay. When you have a flame under compression, they will give you a different feature for heat diffusion. In this case, the thermal diffusion from the surrounding will diffuse into the center region of premixtures, which means the initial flame surface is large, but you diffuse to a small surface of your preheating zone, then the heat is more concentrated to a small region. Then this is a good one because you force your thermal energy to more concentrate to a small region. Then this is a positive effect, just has a opposite effect compared with the case for the outwardly propagation spherical flame. Similar way, mass diffusion now, they will create a negative effect. They are just oppositely be introduced as a previous case. Then you will have a different conclusion. For Lewis number bigger than 1, now the heat is a positive influence is stronger than the negative. In this case, the flame is stronger. Okay, when you have a inwardly propagating spherical flame with the Lewis number larger than 1, the flame will become stronger, and when they shrink to the center region. Okay, but for the case of inwardly propagating spherical flame is unusual situation we certainly observe in real application. But this just give you the idea when you think about the problem, focus on the flow under compression, then you will have a different results if you consider the Lewis number. But for the left-hand side, actually, this flame propagation outwardly under positive flow stage, then their behavior should be the same as that for a premixed flame propagating in stagnation point flow or opposite jet flow. Okay, this will give you the example for the case. For these 3 cases, we can discuss together. And in the left-hand side, they show you this is for, let me see. Oh, this is for hydrogen air mixtures. The evaluation for hydrogen air premixture is very the same with the methane air premixture. You can try to evaluate the Lewis number by yourself. And on the right hand side represent propane air premixtures, and they do the these kinds of calculation and experiments, and you will find out for the opposite flames, outwardly propagation spherical flame and inwardly propagation flame for these 3 different cases, and you understand the previous 2 they should be the same. They should have the same variation on changing the stage and the different Lewis number, because these 2 kinds of flames are under positive flow stage. But the last one basically is the flame is under the negative stage under compression. Their results should be different compared with the other 2 cases. Okay. And for each figures, actually the horizontal axis represent the stage rate you increase. Okay, and the vertical axis represent the burning velocity. Okay, they identify. Okay, here they starting from the zero stage. That means that this is will be the ideal case. Okay, then they do the experiment that you find out for opposed jet flow, opposed jet frames. As you remember, for Lewis number smaller than 1, for the lean hydrogen, this is a smaller than 1 y equal to 0.6, right? Lean, as the lean case, we already estimated Lewis number should be smaller than 1. But for the propane, the lean case here, okay, the lean case is here, and this is a rich case. And we understand for the rich propane air mixture, they are the Lewis number corresponding smaller than 1. These two are for the lean hydrogen and rich propane, they should have the same Lewis number value less than 1. Okay, here this is a Lewis number smaller than 1. But oppositely, for the rich hydrogen and lean propane, they do have the case for the Lewis number larger than 1. Okay, now we look at the results. For the case of Lewis number smaller than 1, here lean hydrogen flame and the Lewis number smaller than 1 reach a proper flame. You can see as you increase the flow stage, the flame speed is increased. Okay, here the flame speed is increased. Okay, the flame speed is increased. As you remember now, you understand the opposed jet flow. In this case, more than 1, that means the negative thermal effect in the numerator and the positive mass diffusion effect in the denominator, positive stronger than the negative effect. That means for Lewis number, the burning strength will be increased continuously. Okay, here this is increased. Okay, conversely, you can imagine for the Lewis number bigger than 1 case, for the rich hydrogen and lean propane, when their Lewis number larger than 1, that means the negative thermal diffusion is stronger. Then when you increase the stretch, then the flame speed will continuously reduce for both cases. Okay, you try to think about a little bit, because it is when you follow my explanation, it is sometimes too fast. You need to have some condense your idea to look at the behavior, and you believe for the opposed jet flame case, compared with the outward propagation spherical flame, you should have the same result, right? Here, Lewis number smaller than 1 corresponding to the lean methane, Lewis number smaller than 1 corresponding to rich propane, completely the same with the previous two, and their result tell you the burning intensity is increased continuous with the flow stretch. Okay, you try to think about it. Okay, and the last the last samples examples is inward propagation spherical flame. That means that you need to think about the burning catalyst. Basically, is opposite from those described in the previous two cases. I give you the one case explanation here. For Lewis number smaller than 1, in this case, because the heat diffusion becomes a positive, then if the heat diffusion in the numerator is a positive, but it's weaker. Okay, no, I'm sorry, it's stronger. Sorry. The Lewis number is basically the thermal diffusion divided by the heat diffusion divided by the mass diffusion. But in this case, the heat diffusions, the mass diffusion is stronger, but mass diffusion is a negative effect. That means the stronger negative effect in the denominator compared with the weaker negative effect. That means that the flame burning strength will be reduced if you increase the stretch. Then you can see they are continuously decreased. Okay, this is the 3 cases we just described, and I let you understand the results is be confirmed from our descriptions. Now we go to a typical frames used for the compression. actually the Bunsen flame, right? Okay, the behavior for the Bunsen flame should be the same with that for the inwardly propagating spherical flame, because both of them under flow convection. Since when you look at the Bunsen flame along the actual coordinates, the flame surface continuously reduced, then that means the flame surface is under compression. In this case, you can see on the tip of your Bunsen flame, you can see here, when you have a fresh premixture from the upstream side, moving, when they approaching to the edge of preheating zone, okay, now they try to have a diffusion to the flame zone. You can see now here, the mass diffusion is diverse, right? It's diverse. We can redistribute for a large region. In this case, mass diffusion is negative effect. But for the heat diffusion, they will have a concentrate effect. Then you will have more energy distributed in a small regions. Then this is a positive effect. Then the result tell you if Lewis number bigger than 1, the denominator you have a positive, stronger positive effect compared with the weaker negative effect represented by mass diffusion. Then you will find out mass heat stronger than the mass, positive effect larger than the negative effect, the flame becomes stronger. This behavior is completely the same with the previous case for the inwardly propagated spherical flame, but it's just completely opposite compared with the case for the stagnation point flow. Yeah, because the basic reason is the case A, stagnation point flow is under positive stretch, but for the case B, Bunsen flame is under negative stretch. Okay, and this is a typical, very nice experimental result I tell you. Okay, and when you look at the experiment, they tell you, we try to give you the 4 cases with different concentration for methane. For lean case, 9% is a lean, 12% is a rich. Propane, 5% is the rich, and 3% is the lean. And you can estimate the Lewis number as we did previously. You will find out for the Bunsen flame, lean methane flame, Lewis number smaller than 1, we already explained, and the rich one is smaller than 1. For these two, you will find out when you do the experiment, you find out on the tip, when you do the measurement, you will find, or you do the some, you take some view from the top, you will see there is a hole occurs on the tip. There is an open hole. Open hole means there is no flame exists, which means flame extension at this point at the on the tip. Why? Because Lewis number smaller than 1 means the denominator, the mass diffusion, the negative effect is stronger than the positive mass diffusion effect. That means the weaker mass diffusion, the negative mass diffusion effect stronger than the positive energy concentration effect, then you will find out the burning intensity is reduced and the negative is too strong. Then they cannot have a balanced supply from the diffusion. Then they will the extinction for these two cases. Both of them are Lewis number smaller than 1. Definitely, you will find out Lewis number bigger than 1. They have opposite effect. When you do the measurement, the flame temperature at this point is increased continuously if you are along the flame surface. Okay, this is a typical example to tell you. There is some nice picture from the previous literature, but they are black and white, but you can see still the same, right? As you Lewis number smaller than 1 here for the figure A and the figure D, there is an open tip, okay? And there is a dim propane and a rich propane. The Lewis number bigger than 1. They have a more intense burning on the tip of the Bunsen flame. You can try to compare, because the arrangement for the pictures and in this slides is just complete difference with this slides. You can try to adjust it, but anyway, the conclusion is for the Bunsen flame, Lewis number larger than 1, then you may have a weaker flame on the tip, and this stronger, and this will cause the more bright on the tip of your flame. And for the case of Lewis number smaller than 1, then you may have an open hole on the tip of your Bunsen flame. And some people do the experiments, especially for the Bunsen flame. You try to think about those kinds of results. In the left hand side, they choose different kinds of fuel, methane, ethane, and propane. Ethane here, you see the molecular weight of ethane is around 28, right? Compared with air, actually, the methane, the ethane, and the oxygen and nitrogen, actually, the molecular weight is almost the same. In a sense, the so-called Lewis number, they always equal to 1, even you choose the lean case or rich case, okay? Now, you can see here, they do the measurement along the flame surface. There is the capital RF represent the position of your measurement point, okay? 5 means you're starting from the base of your Bunsen flame, and you continue to measure. Okay, that means that your RF is continuously reduced. When you reach to RF equal to 0, that means that you are going to the tip of your Bunsen flame, right? Okay, now you can see from this video, for example, the first one for the methane. As I mentioned earlier, for the lean methane here, 0.82 Lewis number smaller than 1. As we analyze for the flow under negative stage, Lewis number smaller than 1 flame should be weaker continuously, right? Initially, when you the measurement point closer to the port, as I explained earlier, there is some heat loss to the port. The temperature should not too much, should not too high. Okay, starting from the 1400 degrees Celsius, but now increase, and then they keep almost the same, almost steady. But when they approaching to the tip, you will find out actually the flame is more, the flame surface is more focused, right? But actually the temperature is reducing on the vicinity of the tip. Okay, and for the case of a rich case, Lewis number bigger than 1. Now the flame we expect is become stronger. Okay, then you can see this line starting from the very close to the 1500, and they continue increase to the maybe 16 and 30 or 60 centigrade degree of Celsius. This represents on the tip of your of this flame, the flame temperature is increased because flame is become stronger. Okay, corresponding to the conclusion based on the distribution of the Lewis number bigger than 1. When you use the equation equal to 1, that means that under stoichiometry ratio, actually they do not have a significant effect for the Lewis number very close to 1, then the temperature will keep the same. Okay, this is a typical behavior. You can explain it based on the Lewis number for this Bunsen flame under negative stretch. You can try to think about the variation of flame temperatures described in the in the loader figures, and for the propane air mixtures. I will not explain it, but you can see they should have a opposite effect based on our previous Lewis number analysis. Okay. Now go to the right hand side. Okay. Then they try to change the equilibrium ratios. Okay, equilibrium ratio, and do the measurement on the tip temperature. On the tip temperature only, try to vary the equilibrium ratio to see the differences. Okay, and the upper one represent the methane air. Okay, here they tell you for the lean, for the Lewis number, for the lean equilibrium ratio is more than 1. In this region, Lewis number usually is more than 1, as I explained. And you can refer to the figure in the left hand side, right? The flame temperature is reduced. Okay, here this is an experiment result. They use this experiment result compare with the theoretical prediction. This is theoretical prediction without considering any heat loss or flow stretch. It's a adiabatic flame temperature. Okay, here they tell you if Lewis number is more than 1, which means the flame is under negative stretch, and also Lewis number is more than 1, the heat diffusions, the negative heat diffusions, I'm sorry, the positive heat diffusion is more than the negative mass diffusions, then you will the flame will suffer by the flow stretch coupled with the Lewis number. Then the flame temperature should lower than the adiabatic flame temperature, arbitrary in the rich sites. Okay, and the positive heat influence overcome the negative mass. Okay, then the flame becomes stronger. Now you can see in this case, in the rich site, the experimental data is higher than the calculated adiabatic flame temperature. And a similar way for the propane air, you can see the behavior is reversed for the lean case and the rich case. You can examine it by yourself. But for the case for the SN, here they tell you, since we do not have a significant Lewis number influence, because Lewis number always equal to 1, because molecular weight for the ethane and the air, the nitrogen, oxygen in the air is almost the same. They do not have very significant difference for Lewis number. Now, the overall, the flame temperature for lean and the rich case is also always smaller than the adiabatic flame temperature, because this may be caused by some heat loss to the surrounding, since the calculation for adiabatic flame temperature is under adiabatic case. But in our experiments, in reality, we need to face a certain heat loss to the surrounding or to the burner. But they just have a shift a little from the ideal adiabatic flame temperature. Okay, this is a good experiment to tell you how to do the comparison for the case, different kinds of flame under various flow stretch. And did remember these figures basically described by using a Bunsen flame. We do the measurements along the flame surface, try to figure out the variation of flame temperatures on the flame surface along the actual coordinates. Okay.